Today, we're starting off with some fun with fractions. For this first thing that I'm going to do, I really wouldn't even bother taking notes. This is just, I'm going way back in time to talk about multiplying fractions. And then we will fast forward to talk about multiplying rational functions. That's the part where you should be taking notes. Once upon a time, we talked about multiplying fractions. I don't even know if this is how you saw multiplication of fractions. It doesn't really matter. I just want to talk a lot. I want to kind of take this back to previous conversations about what the denominators mean on these fractions. So when I see these, I think of the top number as telling me how many of something we have, and the denominator as telling me the size of the something. When we go to multiply fractions, like 2/3 times 3/4, what this is really saying is if I took one whole thing and I took 2/3 of it, that means I'm going to cut it into thirds in this direction. And I'm going to take 2 of them. And then in the other direction, I've got 3/4. So again, the denominator tells me the size of the thing. So I'm going to cut this into fourths. And I'm going to take 3 of them. Then thinking about multiplication is really finding area. I'm saying that we need the 2/3 in this direction and the 3/4 in the other direction. So all told, the number of things that I end up with is 6. I end up with 6 of those boxes. And then the denominator is the size. Well, because I cut it into 3 pieces this way and 4 pieces this way, the size of each box is a 1/12. There are 12 boxes. So I've got 6 of the 12. And with the heart of it, when we're multiplying fractions, this is like the underlying thing that's happening. But functionally, we're not drawing out boxes. If I see 2/3 times 3/4, I have 2 options. I either think about multiplying straight across. So 2 times 3 gives me that 6. 3 times 4 gives me the 12. Or I could think about rearranging the terms. Because they're all multiplication here, I could regroup things and kind of group that 3/3 together and recognize that, hey, 3/3, that's an invisible 1. And then get down to 2/4, and I can think about 2/4 and either break the 4 apart to be a 2/2, a 2 times 2, so that I get a 2/2 that's equal to 1, and eventually get to this 1/2. It doesn't matter what way you simplify yourself through the fractions when we're talking about numbers, but the point that I wanted to get across is that when we're multiplying fractions, we're multiplying straight across the top to come up with the how many of the thing, and we multiply straight across the bottom to come up with what's the size of those things. If we can multiply fractions, let's just do one more quick multiplication problem with fractions where I'm not drawing it out. So if I had 3/4 times 10/21, I could multiply these straight across and say 3 times 10, that's 30, 4 times 21, that's 84. And then somehow try to reduce that to lowest terms. That's never what I would actually do. I don't want to make numbers bigger if I could make them smaller instead. So if I was actually presented with this problem, what I personally would do is to look at that 10 and really see that 10 as 5 times 2. And in the denominator, see the 4 as 2 times 2. And that 21 as 3 times 7. Because it's all multiplication, now I can group the things to find my invisible ones. 3 over 3, that's a 1. And 2 over 2 is also a 1. And I know I made this really messy now, but I'm down to a 5 on the top and a 2 times 7 on the bottom, or 5/14. I don't care at all whether you show work on this problem or not, but what would be important is recognizing that we can get this down to lowest terms. And if we can do it with numbers, then we can do it with polynomials also, where that first step is to think about factoring things out so that we can find those invisible ones to cancel out for us. Well, if we can multiply fractions, we can also divide them. Again, this is just a refresher with numbers, and then we'll get on to the polynomial stuff. 3/5 divided by 15/7. For starters, we honestly almost never write this symbol in calculus, just being real. What we would actually write here would be something like 3/5 giant division bar divided by 15/7. But this takes up way more space on the page. So I think textbooks tend to write it like this, even though we'd almost never write it like this in real life. Okay. Probably some of you remember that when you divide, you flip and multiply, or some other little catchy phrase. I just want to back up for a second to make sure that I never want you to just like take my word for it or take some other teacher's word for it. Back to basics. Math is always built on some small foundational principle, and then we work forward from that. So going back to, I think I used the same example yesterday, but 6 divided by 3 is equal to 2 because 2 times 3 is equal to 6. And if I took that 6 divided by 3 and I rewrote it using this division symbol, that would look like 6 divided by 3 is equal to 2 because 2 times 3 is equal to 6. If I write out that same because statement for our current problem, then the because statement that goes with this would look like, if I'm kind of matching where things are, that 2 was the piece on the side. So I'm going to have, oh, I need a piece on the side because I needed an equal sign. Give me a second. This is equal to, I don't know. If I went out to write that same because statement, this would look like the piece I don't know times the 15/17 is equal to 3/5. Well, if I'm trying to get this question mark piece by itself, it is true that I could divide by 15/7, or I could think about the other way to move this to the other side of this equation would be to take that 15/7 and multiply by 7/15. And as long as I did that on both sides of the equation, I wouldn't have changed the problem. Why the 7/15 over here? So that my 7s cancel out to give me that 1, and the 15/15 cancel out to give me the 1. So the shortcut for how to get to this final answer is to reframe the original question to actually say 3/5 times 7/15 is equal to what?